Okay, so I'm going to briefly talk about this half-baked or maybe even a quarter-baked idea that I've been trying to figure out for a while, and then it's mostly on this intuitive interpretation of use, and I'll explain what I want to get out of a reasonable definition of use and how it's related to ideas like non-interference, and I'll show you some problems that arise were you to use standard techniques to try to capture an intuitive idea of use. So what do I mean by use? So let me show you the picture you've seen probably a dozen times today. Is you have a complicated system with some inputs. Some of them are sensitive in that you don't want them to leak out. In this picture, I'm just pretend that everything is visible to or everything is visible or used in a sort of downstream task. So I want to check whether a input A is quote unquote used in a computation and ends up affecting a value C or D. So I guess the simplest thing you might do in this case is do standard non-interference, which somewhat captures the idea of use, and that happens because, to reason about that, you'd think about two different inputs for A, and they produce two different outputs for C, and if that happened, you'd say there is some interference, which sounds very much like use of A in producing a value C here. So the idea of non-interference sort of captures what I'd want to describe by this notion of usage, but it's not always capturing that. And I'm going to show you the example that I'm more likely to work with is when you have machine learning components in your system that were sort of statistically derived based on some analysis of these inputs, maybe A and B, from some empirical data set. And in this case, it might not be that there's an explicit flow from A to C, but it's sort of implicit from the statistics that sort of were true when this machine learning component was learned. So for example, if A is perfectly correlated with B, and B ends up being the one that's explicitly used in this machine learning component, we might not be able to find that A leaks to C using standard non-interference. But there's other techniques which would be able to capture that. There's quantitative information flow, where you presume that there's some prior distribution on A and B, and you sort of compute the complicated program on these distributions, and you collect the outputs in a random variable C and D, and then you test whether C is independent of A. So this might capture these situations where the use sort of happens through correlation. But the problem with that is, one more thing I should mention is that you can also quantify how much use happens by doing some standard information theoretic measurements like mutual information between random variables. But the problem is that there's this famous saying that says correlation is not causation, and there's a variant of that you can sort of construct, is that you cannot test causation using correlation. So if there is no correlation in something, that doesn't mean that thing wasn't used. So for example, if A is not correlated with C, that doesn't mean A was not used in computing C. So the standard example would be like an encryption. Let's say we have a plain text message A, and maybe B is the key, and it gets encrypted, and C gets output as the ciphertext. And we'd hope from a reasonable crypto system that C and A are not correlated. Yet A was used, quote unquote, used in the computation of C. Right? So these information theoretic or quantitative information flow approaches will not be able to sort of completely capture this idea of use. So what can you do? Well, one reason why this might happen is if A is actually a cause of B. So think about, let's say I work a lot in privacy, and let's say that A is someone's age and B is their height. So maybe someone's age causes them to be taller or shorter. So that makes sense. And that's how correlations might arise. And moreover, if we had a model that told us that A causes B, we might be able to determine whether A causes C if it flows to B and then B flows to C. Right? So even though there's a flow that is explicit from B to C, there's actually this implicit flow through correlation and causation from A to C as well. But there's other cases, for example, A and B can be correlated, but they might not have sort of a causal relationship between them. Maybe there's a common cause of both of them, and that's why they're correlated. So if we had a causal model between these variables and maybe some latent factors like L, we might be able to determine whether actually A is used in the computation C by sort of looking at sort of A and its direct causes and so on throughout the computation. So what I'm trying to do is derive a causal model from empirical observation. So if A and B are some data set, which we're doing machine learning from, can we derive causal relationships between the variables so that we can integrate it into some analysis to be able to tell whether things are used even through statistical correlations? So there's many problems in this. There's latent features which might not even be in your data set. There's under constraint observation. So for example, if A and B are identical, there is no causal analysis that will be able to figure out which one is the cause of the other. So in the end, I think a lot of this will depend on integrating human knowledge. So things like height does not cause age, its age causes height, and so on. And I think if there's a way to sort of develop a reasonable causal model on data, we might be able to apply things like non-interference or this sort of derived form of use that's based on interference and be able to ask these questions of usage of features through a statistical component in a larger system. And that's the half-baked idea. Any questions?